In our last video, we looked at what it meant to have a future value of an annuity, and today we're going to look at what it means to have the present value of an annuity. So, you can see here that we're starting off with the same definition. The fact that this is still an annuity because we're still making equal period payments. Now, we said before that if we were making the payments at the end of each time period, then we had an ordinary annuity. And that the future value of that was the sum of all the payments that we were making into an account plus the interest that you earned. Okay? That's what we were doing last class and on the last video. But we can also think in terms of a present value of an annuity. And for this, we need to think in terms of all of the payments that we want to pay out of an account so that we end up with 0 after a set number of equal payments. Okay, so we're kind of reversing the thinking here. Last class, we were talking about how many payments into an account to grow the account to end up with a larger amount at some future point. Today we're talking about what would I put in right now so that I could take payments out of that account and end up with 0 at some point in the future. All right, so here's the problem, and we're going to change this problem from what's in the book. We're going to make this a little bit simpler to start. So, how much should you deposit in an account paying 6% compounded annually in order to be able to withdraw $1,000 every year for 6 years? And the idea here is to set this up so that after that last $1,000 payment is made, there is no money left in the account. Okay, so pause the video here for a minute if you need to and change the actual problem in your booklet so that it reads like this, because this is what we're going to be doing on this video. Okay, so here's what that would look like. So we are trying to figure out the present value. Let's go back to the present value we already know about. Again, if you think about A being equal to P times 1 plus I to the nth power, right? That's our compound interest formula. Well, if I wanted to solve for P and figure out what the present value should be, then I would have to divide both sides by the 1 plus I to the nth. Okay, so from this then, we would say that P equals A divided by 1 plus I to the n power. Well, another way of writing that same thing is to say that I want A times 1 plus I to the negative n power. Remember, negative exponents are just another way of writing reciprocals. So I can take this, where I have 1 plus I to the nth in the denominator, and I can move it up above the fraction bar by making it a negative n for my exponent. So these two things are saying the same thing. Okay? And this is just a little cleaner version for finding P. So here's the idea. At the end of the first year, I want to be able to make a $1,000 payment out of this account. So the question is, what do I have to put in now as a present value so that at the end of the first year, I will have the $1,000 to make the payment? So we use our present value equation now. We're going to use it in this form. And so the future value I want is this 1,000 and then 1 plus I. So since we're just compounding annually and we're making the payment annually, we're just going to go with the 0.06%. And since this is just 1 year later, I just want a -1 up here for my exponent. Okay, so similar to what we did in the last video, let's just kind of work this out for all 6 years. So at the end of the second year, I want to be able to make a $1,000 payment. So how much do I need to put in right now as the present value to be able to do that in 2 years, to make that $1,000 payment? So that $1,000 payment is going to have 0.6 added to 1, but now it's going to get 2 years of interest included in that. So I'm going to take that to the -2 power. And we can keep going. So for $1,000 at the end of the third year, I'll need to take the $1,000 times 1.06 times, or excuse me, to the power of -3 to figure out how much money I need to put in right now in order to make this particular $1,000 payment. Okay, at the end of 4 years, $1,000 times 1.06 to the -4th. End of 5 years, that $1,000, I'll need 1,000 times 1.06 to the -5th. And finally, the $1,000 at the end of the 6th year means $1,000 times 1.06 to the -6th power. Okay, so this table has helped me to see what I need to do to get that particular payment, and what I need to do here to get this particular payment, and what I need to do here to get this particular payment, and so on. So the present value for the entire annuity then is going to be the sum of all of those. Okay, so this should be sounding familiar because it's the same concept as what we were doing with future value. We want to add all of these present values up in order to know how much I need to put in right now to cover all 6 of these payments and end up with 0 in the account when it's all said and done. Okay, so since I'm looking for the sum, we again are going to go back to writing this as the sum of all of these present values. So that means S is going to equal the 1,000 times 1.06 to the -1 power plus the 1,000 times 1.06 to the -2 power plus 1,000 times 1.06 to the -3 power plus 1,000 times 1.06 to the -4 plus 1,000 times 1.06 to the -5, and I think I'm just going to make it 1,000 times 1.06 to the -6. Hopefully you can see that well enough to know what you're supposed to write. Okay, so this is the sum. This is the present value for this entire annuity, is adding all of these up together. Now again, this gets pretty tedious because depending on how many years or how many periods you're talking about, this can get really obnoxiously long. So we're going to do the same treatment on it that we did with our future value. I'm going to take this and this, and I'm going to multiply both sides by 1.06 again. Now remember, that means taking the S times 1.06, and that means taking every one of these terms times 1.06. So when I take 1.06 to a -1 power, and multiply it by another 1.06, that means adding -1 with +1, and so we end up getting rid of that one. So my first term now here is just the 1,000. And then every other term, I am adding a 1 to the exponent so that the -2 now becomes -1, the -3 becomes -2, and so on. Okay, and then on the left side I have the 1.06 times S. Okay, now just like we did last time, I am now going to subtract from that the original S equation. And you'll see the same kind of thing happens. I have matching terms that when I subtract them, they're going to cancel each other out. So all of these terms are going to subtract from each other and cancel each other out. And so what I'm going to be left with is 1.06S minus S, which is the 0.06S, and then this 1,000 minus this 1,000 times 1.06 to the -6. So the 1,000 from the top equation minus the 1,000 times 1.06 to the -6 power in the second equation. And so now we do the same thing. We want to rewrite this in a way that's going to get us the formula for a present value of an annuity problem. So we're going to start by factoring out the 1,000, because again it's common to both this term and this term. And this time when I do that, I end up with 1 minus the 1.06 to the -6th. So same terms, but this time they're in the opposite order that we had from our future value. That's all still going to be equal to 0.06S. And so now if I divide both sides by 0.06, I end up with a formula that looks like this. S equals the 1,000 times 1 minus the 1.06 to the -6 over 0.06. So that's how that all simplifies down into the formula. So again, using that to get our general formula, our sum now represents the present value. What do I need to put in now to be able to cover all these payments that I want to make? So my present value is going to equal the 1,000. That is the periodic payment that's being made out of this account. So PMT still stands for payment. We just have to make sure we understand that we are paying out of the account rather than into the account like we were for future value. And then that's going to be multiplied by the fraction. And in the fraction, I'm going to have 1 minus, and then in parentheses, my parentheses are 1 plus the I. So the inside of the parentheses is still the same. It's still 1 plus I. And that is still going to be taken to, let's see here. That's still going to be taken to an n power, but remember it's negative n now. Okay, and then all of that is still going to be divided by the I, which is what the 0.06 was. Okay, so this now is the formula. Oops. This is the formula for present value of an annuity. The amount I would have to put into an account right now so that I would cover the future payments that are going to be made over a specific amount of time, equal payments being made at the end of each period. We still have to remember that that's key. It's the end of each period. And end up with a total of 0 in the account when it's all said and done. Okay? We'll look at a couple of problems on how to use that when we get together in class. So please make sure you understand what this formula is, what the pieces of the formula are, so that we're ready to use it together in class when we get together next time. And until then, have a good evening. We'll see you in class.